Okay, we should be streaming. Hello, everyone. My name is Joanna Wu, and with me is Kyle. Say hello, Kyle.
Hello, hello, hello. Good evening.
I hope everyone. Oh, let me just
Okay.
stop that. Okay, I always have to stop my YouTube whenever that helps. Okay, so with me today, so we have Kyle, who is a longtime staff member of the Observatory. My name is Joanna Wu, and I am the director of the Trottier Observatory, also a lecturer in the physics department at Simon Fraser University. And we also have today moderating in the chat Douglas from the RASC, from the Royal Astronomical Society of Canada Vancouver branch, so welcome, as well as Zach and Rohit, who are longtime staff members of the Trottier Observatory. So thank you, moderators, for coming and helping with moderating the chat. So if you have questions tonight about anything, please feel free and ask your questions in the chat box, and either Kyle or I will have a look at the chat once in a while, but we might be busy chatting and fiddling with the images. So the moderators will be there also to be paying attention to your questions and answering questions for you. So I'm excited because tonight it's so clear, it's gorgeous out there, and we've got a nice list of really beautiful objects. There is a full moon tonight, unfortunately. I mean, well, depending on how you look at it. Fortunately, because we can look at, well, the moon it's a little bit too, we're not going to be able to see the moon tonight. It's too low to, below, like it's too close to the horizon. But it'll be up just enough to make things too bright. But there are lots of objects on the opposite side of the sky from the moon and lots of really bright objects. So hopefully we'll be able to see lots of fun things tonight. So, so the first thing, we're actually already pointed at it, the first thing we're looking at is the star Vega. Now, the sky is actually, since we're so far north here in Vancouver, 49 degrees, right? That's the border, so we're even more north of that. Because we're so far north, the sky stays bright forever in the summer. And the sky is still actually quite light right now in the sky. You can see the camera, the western looking camera, that's the middle one on the left on your screen. You can see that sky is still a little bit light. It's kind of crazy. But there are lots of stars that are visible, including stars that are visible in broad daylight. And we're looking at one of them, Vega. The star Vega is visible in broad daylight. It's kind of weird to think about. There are actually lots of stars that you can see. And this is one of them, but it's not broad daylight right now, but we're looking at Vega. Kyle, why don't you tell us a little bit about Vega?
Yes, okay, so just to start us off, for those of you that have seen the movie Contact or read the book, Vega should be a familiar name. It is the star that the extraterrestrial used to contact Earth from. And pretty much what happens is they just returned a signal that was sent out into space because as we're communicating with radio and watching TV, phone calls, all that kind of stuff, those signals don't really travel in a straight line. They actually travel spherically. And as a consequence of that, our radio signals are traveling into space as well, is where we want to go. So what happens is we've been essentially broadcasting ourselves. I'm just taking an aside for extraterrestrial stuff for a moment. I'll get back to Vega in a second. But so pretty much our signals have been traveling into space for pretty much ever since we invented the radio technology. And as such, anyone who might be listening within, this is a good question. I'll say, I'm sure someone will correct me. Probably 100 years or so, or maybe a little more. Whoever's been listening within 100 light years of us would have picked up our signals and maybe have sent a response. We'll see. But that was the plot of the movie, is that these extraterrestrials picked up our signals and simply just replied and returned that signal back to us. But getting back to Vega, I won't spoil anything, even though I spoiled Aliens, but I won't spoil the rest of the movie. But yes, Vega itself is 25 light years away, so it takes light 25 years to get there. And as such, any broadcasts that we've been sending out 25 years ago, if there was any extraterrestrials in Vega, they'd be getting it now. So, kind of fun, kind of interesting. But what Vega literally translates to, or roughly I should say, is for sweeping vulture or eagle, since the Lyra, which is the constellation that Vega is in, was represented as a bird in several cultures, when now it's actually just represented as a musical instrument, like a lyre. Anyway.
But what language was that, Kyle?
I think, I think Latin,
Latin,
was it?
Huh?
Or Greek. Probably Greek.
I didn't know that.
Greek mythology, yes, Greek. That's the other cool thing about things in space is they're named, like there's Latin in space, there's lots of Greek, even some Roman in there, like our planets, Jupiter.
There's also a lot of Arabic as well.
Sorry?
There's also a lot of Arabic as well.
Oh, Arabic as well, like all of these languages are represented in the night sky, which is awesome. But yeah, like Jupiter, Saturn, they're all Roman deities, with Pluto and Charon as well. But anyway, lots of languages represented in space. But again, trailing as well. Going back to Vega, it was the first star to have its spectrum photographed, and I mean the reason for that is because it was so bright. Like what Joanna said, is we can see it in broad daylight. It is actually our reference star for the brightness magnitude scale. It's pretty much it's a 0.000 magnitude, which is awesome. So everything else in the sky we base off of Vega. And just as another aside, just to give an idea for the magnitude scale, it is a logarithmic scale. So something that has a magnitude of 2 compared to a magnitude of 1 is something that has a magnitude of 2 is 2.5 times dimmer than a magnitude 1 thing. And just to give you an idea, our sun has a magnitude of negative or minus 24. So it is pretty much the brightest thing in the sky. But that's kind of how this magnitude scales work. Negative is brighter, and the more positive is more dimmer. But yes, Vega, it is really, really big. It's 2.3 times the mass of our sun. And it kind of has a large radius bulge at the center. And okay, so what that means is, it is spinning so incredibly fast. Like it's spinning at 274 kilometers per second at the equator, which is it's wicked. Our sun has comparatively is spinning at about 2 kilometers per second at the equator. So what happens is, because it's spinning so fast, it wants to flatten out. So that's why there's this little bulge at the equator, that like a central bulge all the way around the star, is because it's rotating so fast. 93% of its breakup speed, which is pretty much if it spun any faster, it would just kind of fly apart.
Well, that's really fast.
What else?
Cool. There's another star I want to tell you that is spinning also really fast as well. But that's cool that Vega's like that as well. Cool.
Oh my god, I know. And what was I gonna say? Yeah, speaking of like rotational speeds, like stars can spin so fast. Like I don't think we won't be able to see any today. I don't think, but there's these things called pulsars in the sky, and those are the corpses of dead stars. And what's happened is, when they exploded in supernova, the core that was left over just shrank, and like a ballerina pulling in her arms, it just spun faster and faster and faster, and you can get to some pretty incredible speeds when you get to pulsars. And magnetars and all of these freaks of nature in space. So really, really cool. But unfortunately for Vega, going back to the whole contact inspiration, there are no planets that were observed, but there is likely a debris disk rather than a protoplanetary disk that's circling around Vega. So this what was it? This debris disk. It's not like dense enough to create planets like a protoplanetary disk is, but this debris disk is still probably about as dense or a little more dense than the asteroid belt. So some potential, but I don't think it's dense enough. So.
All right. Wow. Okay. Cool. Yeah. Vega's,
lots of cool stuff.
There's lots. I also remember somebody had pointed out, and I think in a previous Starry Nights that I had watched, was that Vega used to be the North Star. Is that?
Yes.
It was so. The Earth is spinning right on its axis, and that's why we get day and night. But because just like a top, when you spin a top on a table, it wobbles a little bit. In the same way, the Earth's axis is also wobbling. And the reason for that is not because there's friction in space, but it's because of gravity, the interaction between the moon and the sun and the Earth actually causes the spin axis of the Earth to wobble. And so right now, our spin axis, the northern pole, is pointed toward Polaris, the current North Star. But in the past, it had been pointing towards Vega. So Vega used to be our North Star. But that was like a long time ago, something like 12,000 years ago. Am I right? Kyle?
Yeah, no, like the complete cycle for precession is, 26,000 years
That's
to complete,
right, yes.
to go around once, right? So, oh geez, what was happening 12,000 years ago? The beginning of human civilization, pretty much. Like in Mesopotamia, Vega was the North Star, and now 12,000 years later, Polaris is now the North Star. Kind of cool.
Yes, very cool. Well, thank you for describing Vega for us. So isn't that pretty? So look right now, we're exposing every, whatever it is, 800 milliseconds, and you can see the glowing spikes just move. I think it's just so pretty. I mean, bright stars are very pretty. Here, I'm just changing the contrast a little bit so you can see the spikes glow. It's just so beautiful. Anyway, stars are pretty. They really are like diamonds in the sky, aren't they? Okay. So I think I am happy to move on to our next target, which we haven't looked at in a long time, I've noticed. And it's a star called Alberio, which, by the way, is Arabic, or it was supposed to be Arabic, but apparently it was kind of a mix between Arabic and Latin or something. But where is it? It's in the constellation of Cygnus the Swan. So if you see here, here's the Swan, right? This is also called the Northern Cross, because you normally see just this part of the stars. Most people recognize this. But it's Cygnus the Swan. So you can see these are the wings of the swan, and this is the neck, and that's the head. So it's the head of the swan, Alberio. And that's the star we're going to look at now. And it's quite a well-known double star that has two stars of very different colors. So I'm going to show it to you, and you're going to tell me what you think. Oh, look at this. Isn't that gorgeous? Isn't that gorgeous?
Oh, that's
I'm going to
awesome.
make it a little bit lower. No, I think, that's all right. That's all right, I think. Okay, can you see, by the way, can everyone see the color difference between these two stars? I know there's a little bit of a lag between us and the chat.
Just watching the chat. Oh, take your bets. which one, and moderators and brass people, don't say anything, but which one do you think is hotter?
Yes, great question. Which one's hotter?
Let's see what people think.
Wait, do you see the different colors, first of all? I mean, I can see the colors, but I don't know how it gets through onto YouTube.
Maybe. I think I can see the colors. I think they're pretty... Ooh. Yeah, just looking at the stream, there's a little small difference. It's not as pronounced as looking through the telescope, but...
yeah.
Which is, of course, the... Great. Oh, yes.
Yes.
Okay, so
people are saying that there are... Okay, people can see the different colors. Okay, good.
Blue and orange. Okay, good.
Blue and orange. Great. And somebody guesses that the blue one is hotter. Do we have any other votes?
Left equals hot. Your left is the blue one. Okay, another vote for blue.
And the one on the right is a bit orange. That's right.
A bit orange, okay.
Great. So we do have a couple of people voting for blue, or at least 4 people voting for blue being hotter. And that was the correct answer. So very good. And in fact, so for just like a blue flame is hotter than an orange flame, it's not exactly the same physics, but the something that is really hot shines. Everything glows, actually. We all glow. Humans glow. We glow in the infrared. We're not very hot. We're only 37 degrees Celsius, and we glow in the infrared. So, when we go to the store now and they take a temperature of, like, they point at your forehead and they take a temperature, that's because they're reading your infrared light, and they're reading how hot you are from your infrared light. But if you were shining hotter, let's say you take a ball of steel and you put it in the oven and you heat it up to, 200 degrees Celsius, then it'll shine.
100.
It'll shine even higher. It'll go, like, instead of the infrared, you'll start to see it glow in optical. Well, actually, it needs to be hotter than that. It needs to be a few thousand degrees in order for it to start glowing in the visible wavelengths. So the sun glows in the visible wavelengths, obviously, and it's the surface of the sun is something like 5,000, 6,000 degrees Celsius. But if you get an even hotter star in the tens of thousands of degrees, then it starts to glow bluer. And then if you're even hotter than that, then you're going to start glowing in the UV instead. So if the star is bluer, that means it's hotter.
Are there any UV stars? I don't think so. Are there any stars that are that hot?
Yes, there are. So, like, for example, the O stars and the B stars. O stars in particular. O stars are the ones that glow in the UV, and white dwarfs as well. White dwarfs and O stars glow in the UV. But of course, you can also see them in the visible. Like, you see the part that's blue. There's not very much shining in the red, but there's a lot shining in the blue, and there's a lot more in the UV, but you just don't see it. You know what I mean? But it still glows in the blue. Fair. So O stars glow in the blue. So a lot of them glow in the UV, and it's those O stars, because they glow in the UV, they're able to break apart hydrogen atoms, and we'll get to that. We'll get to that when we talk about the nebulae. So, but right now, these 2 stars are not one of them. So this star is a B-type star, and this is a K-type star. Now, what in the world are these letters? There was a sequence. Now, there's no rhyme or reason. Okay, there was some rhyme or reason to it. A lady by the name of no, I'm blanking on the name. I'm blanking on her name at the moment.
Hold on, I'll look it up.
There were
if someone in the chat doesn't say.
At Harvard University, there was a astronomer named Edward Pickering, and this was about in the turn of the century, about 1900, around that period. He realized that it was a lot cheaper to hire women than to hire men of the same education. In order to do all this astronomy work for him. So he hired a bunch of women for cheap. Unfortunately, the world has improved since then when it comes to gender fairness, but we still have some ways to go. But anyways, back in those days, and it wasn't just astronomy, that lots of fields realized that they could hire women for cheaper even if they were the same education as a man. So they started hiring, anyways, Edward Pickering at Harvard Observatory was hired a bunch of women to look at stars, and in particular to look at the content of the stars. And this one lady, Fleming, that's
Henrietta?
her name. Fleming. Oh. No. Fleming categorized the stars and called them A, B, C, D, E based on the strength of the signature of hydrogen in the starlight. And so she categorized them by A, B, C, D, and E. But then another later on, a colleague of hers named Cannon. Her name was her first name was. Why am I blanking on these names? Her last name was Cannon. Okay, so
I'm seeing Morgan Cannon's system. Yeah, exactly.
There's Annie Cannon. That's her name. Annie Cannon. There's a famous prize named after her for women astronomers. Anyways, Annie Cannon, she realized that it was actually way more useful to categorize the stars by temperature using like color, and so she noticed that. And then anyways, she took the same A, B, C, D system, but then resorted them by temperature, and then so then the sequence became O, B, A, F, G. How does it go? Okay, there's an acronym, a mnemonic.
Oh, it's this is from Howard.
But okay, in my Physics 190 class, I always ask them, every time I tell them, okay, come up with your own acronym, because the original acronym is a little bit creepy, so I'm not going to repeat the original acronym. But they come up with a bunch of their own acronyms, and my favorite one that my first Physics 190 class, my favorite one, their acronym was, "Only bright astronomers find galaxies kind of mesmerizing." So it was a good thing I didn't know who that person was, because then I would have given them an A, although I don't, actually they may have already gotten one, I have no idea. But anyways, I really loved that acronym because I'm a galaxy specialist, so I really loved that. Oh, only bright astronomers find galaxies kind of mesmerizing. OBA.
I think the other one that was oh boy, an F grade kills me.
That's right. That's another one. Yes. Oh boy, an F grade kills me. Yes. But anyway, so that was the sequence of temperature, and so O stars are hotter than B stars. So this one here on the left is a B star, and then K is the second coolest. So K is the coolest. So that's why it's reddish orange, right? So that's blue, and so it's a hotter one, a B star and a K star. Wait, did I get that right? Yes. Okay. So what's cool about these stars is that, okay, they are right next to each other almost, but we're not really sure if they're an actual gravitational binary star or if they're just happen to be optically aligned. Even with our latest measurements from the Gaia satellite, which is absolutely amazing. The Gaia satellite, the data, go and look at the Gaia website, is absolutely stunning. Some of the measurements that they've made. But anyways, it's okay. But even after the measurements and the measurements of distance of these stars from the Gaia satellite, we still don't really know if they're a physical binary or just an optical binary. If they are physically connected through gravity, then their orbit is something like their orbit takes more than 100,000 years to complete. So we're still not very sure. So the K-type star, that's the orangey one, is a giant star, and it is it's cooler than the other one. And the reason is because when a star expands into a giant, then the outer layers become cooler because they're farther away from the source of the heat, which is the center of the star. Now it's expanded to something like 70 times the radius of the sun, so it's a giant star. And what's cool about this star is that this star itself actually is a binary system. And in fact, it was first discovered because when you take a look at the light of this star, you can see a red shift and a blue shift that's periodic. It kind of goes back and forth. So if you remember what a redshift and blue shift is, you just watch that episode from Big Bang Theory where Sheldon dresses up as the Doppler shift. It's hilarious.
Oh,
his costume makes absolutely no sense, by the way. Like, if you look at it.
Yeah. But just brush past that.
So all of you learn what the Doppler shift is and improve upon his costume for next Halloween. But in any case, yes, the Doppler shift. What is the Doppler shift? It's when waves compress or stretch depending on the motion of the object that's emitting the waves. So when the star is moving towards us, the light will be compressed a little bit so that the signatures of hydrogen will look like they're bluer than they normally are. We don't actually, it's not enough, like the motion is never enough for us to be able to see a shift in color with our own eyes. Like that just doesn't happen. It's far too sensitive to that. But when you measure it with sensitive instruments, you can measure the motion of the star. And because of that, we've been able to find out that this star is a binary star. There's a little companion, which is kind of nice. And actually recently, astronomers have been able to resolve that binary star using a special type of telescope called an interferometer. But anyways, that's a little binary star. So this one might be related gravitationally, or maybe not. But in any case, that definitely is a binary. There's one that you just can't see here. Okay, another cool thing about this star, this B-type star, is another one that's rotating really fast, just like Vega. So this one is also rotating at something greater than 250 kilometers per second. Okay, so like I remember, so what the speed limits in Canada are something like 120 kilometers per hour, right? Like on the highway, but this is 250 kilometers per second. I remember.
I don't know what's
the fastest I've ever. I've driven once in Germany. You know, they have these highways called the Autobahn. I don't know if you've ever been there, Kyle, but it's amazing. Like they don't have speed limit. Like it's unlimited speed on the Autobahn, and it was so scary.
Oh
I drove at like 100. I think 160 was the fastest I drove, and I was like the slowest person on the road.
Yeah, I think they even people behind you, like if they're going faster, they'll flicker at you to say, move out of the way. I'm coming through.
It was so fast, but that's nothing compared to the rotation speed of this star. So, and as well as Vega, I just learned today that Kyle just told us that Vega is also spinning that fast. But this star, this is a B-type star. So Vega is an A-type star, but this is a B-type star, which is more massive. It's rotating really fast. And it's rotating so fast that it actually ejected a bunch of hydrogen gas into orbit around itself, and that hydrogen gas is emitting a special light signature that you can see if you have the right instruments, and so that's why we can tell that it's one of those types of stars that's rotating really fast, that's ejected a bunch of gas into space. So,
wow.
Yeah.
So hold on. So 200 and sorry, what was it?
It was something like 250 kilometers per second.
250. Is that like here to? Oh my god, I don't know.
200. Oh, good question.
Like Okanagan? Is that like almost 300 kilometers away or something?
That's a good question. Can somebody look that up? I have no idea.
Yeah.
How far
Well, anyway, like pretty much, I'll just say here to I don't know, like the top of the Coquihalla, like the peak, wherever that lookout is, in 1 second. Like, no, I don't think so.
Yeah.
That's incredible.
Yeah, it's pretty fast. Pretty fast stuff. So that was Alberio. Oh, how are people doing in the audience?
Oh my god, just looking at chat, lots of chatter. That's all good. Yeah, Lee's saying, so Lee's saying that from Rask, still saying you still get a speeding ticket on the Autobahn if a police officer thinks your driving skill is not sufficient, or if your vehicle is not up to the speed. So,
okay.
Oh, you didn't? Oh.
Yeah, well.
So lucky.
I never got a ticket on there. We were driving all day because we were trying to get somewhere. Yeah.
Oh yeah. Oh my gosh.
Anyways.
Wow. Wow.
Merritt, thank you. Thank you, Rohit. Vancouver to Merritt is around 300 kilometers. So that in 1 second, that's the speed of this rotating star.
Oh
Unbelievable.
my gosh.
Okay, it's 10:30, which means that the sky might be dark enough for some cool objects. So let me be honest here. There's most of the items on our list for tonight, we have tested and we know they work. But I wanted to try an object that now would be the best time to see that I haven't tried yet, so I won't know if it actually works. So I'll be perfectly honest, but I'm gonna try it anyway. I'm feeling a little bit ambitious. There is a full moon, but it's really low in the sky at the moment. I want to take a look at the Whale Galaxy because it's in the west at the moment. So the sky should be pretty. Wait, let's take a look at how the sky looks like in the west. Yeah, it's pretty dark. Let's go over to the west and let's take a look at the Whale Galaxy. It is an interacting galaxy, and I just wanted to throw a galaxy in there because I do like galaxies. And
Kind of what you do,
I do like galaxies. And it's interacting with another galaxy beside it called the Hockey Stick Galaxy, which I figured is pretty Canadian, Another name for it is so there's the Whale Galaxy, which looks like a whale, and then there's the Hockey Stick Galaxy beside it. The Hockey Stick Galaxy is also sometimes called the Crowbar Galaxy, and they're interacting with each other. They're about to merge, which is kind of fun, and it would be cool to see it. So I don't know. I can't promise you that we're going to see it, but I'm going to try and see it because I haven't tested this out ahead of time, but let's give it a try.
High risk, high reward.
That's right.
Let's see what we do it. So 20 seconds, yeah. So just a quick comment on some of the exposure times. So when we're looking for really dim objects like galaxies and nebula, we kind of have to crank up the exposure time. And that's pretty much what that means is leaving the shutter open for, in this case, 20 seconds. Whoa.
Wait, no, I'm just playing with the...
Oh, okay.
Don't mind that.
Fiddling around. Yeah, like for this object, there's this little tab exposure that we're leaving essentially the shutter open for 20 seconds to gather as much light as it can. But for nearby objects like Vega and Alberio, we didn't need to have the shutter open for that long because stars emit so much light and also they're so much closer that we don't need to have the shutter open. I think like a normal shutter camera is like half a second. So for something like stars, we can just have the normal shutter speed like usual. But for something like a galaxy, like we're trying to get now, 20 seconds is what we want, or even more. Is there like a little haze to the left of that?
Yeah, that's not it.
Just to the left?
It's right here, this diagonal thing right here. And, I mean, I can barely see it, but that's what I get for trying to experiment today. But,
part of science.
It's part of science, that's right. Whoops. Yeah, no, that haze is very likely because it's kind of in the northwest. But this, anyways, this is it right here. But I'm just going to let it stack a little bit to make it. It's not stacking. Just a second. Let me see.
Yeah, looking at the chat here. Alexander, yeah, atmospheric conditions. That's what happens. Like a little haze like this, and because we have this exposure time to like 20 seconds, that means any little bits of light like reflecting off of the clouds will come back at us. And
that's true. There's a little bit
screw
of
things up.
Yeah.
Mm-hmm.
Well, okay, I don't think this was gonna work. There's a little bit there's a bit of light pollution on this side, which is this is the northwest side. So there's quite a bit of light pollution all over campus, actually, unfortunately. But yeah, and this is one I didn't try ahead of time, so I didn't know if it would work. But I just saw that it has a very high, like it's a bright galaxy, so I wanted to see if it would work. I guess this was not going to work, but that's okay. We have a lot of things on this list that we know will work, so we won't try this one. Okay, let me just quickly see. The Crowbar Galaxy is supposed to be a little bit brighter. Crowbar or hockey stick? No, then hockey stick galaxy.
Lovely names. Just name it how it looks like.
Yes, exactly.
Oh gosh.
I'm being very optimistic, I know.
Yeah. But still,
yes,
galaxies
I'm
look
being extremely
phenomenal.
optimistic. But here it is, right? It's now pointed in the other direction. But I know you're wondering how can I see anything in all that fuzz? It's experience. It's just experience, seeing fuzzes and recognizing things, what fuzzes should look like. Okay, well, that didn't work. Let's move on then. You know, I know these other ones, these other things are much brighter, and I think let's move on to the Swan Nebula, which is quite a bit brighter. It's in the south, and it's in the it's in near the center of the Milky Way. Let me zoom out a bit so you can see. I put on the Milky Way here in the sky. The Milky Way is gorgeous. It's right overhead, and in the summertime, it's basically almost exactly overhead, and it'll move overhead, over the few hours. It's almost exactly overhead at midnight, and it'll just move across the sky. And the Milky Way is so beautiful. This here, the Sagittarius, this constellation right here is Sagittarius. You can recognize it because if you zoom in on it, you can recognize this this group of stars that looks kind of like a teapot. It's actually called the teapot. The constellation officially is called Sagittarius, but this unofficial grouping of stars, which is called an asterism, is called the teapot. And what's cool is that if you're out in the countryside or in the camping or something, you can see the Milky Way kind of rising from the spout, and it looks a little bit like steam coming from the teapot, which is kind of fun. And this area is the center of the Milky Way. Now you can see the Milky Way spans obviously all across the sky. We're living inside of it. It's like a plate, right? In fact, it's much thinner than a plate. You know how thin the Milky Way is? The Milky Way is as thin as a CD or a Blu-ray disc. Actually, you know what? Are there people here in Generation
Blu-ray
Z?
disc.
Well, I figured,
I don't
know if Generation Z knows anything about CDs. I don't really know what a CD is.
Oh, jeez. I feel like it came and went, like, so quick. Anyway.
Yes, Blu-ray discs, okay? The Milky Way is as thin as, at least, like, the star-forming region of the majority. The star-forming region of the Milky Way is as thin as a Blu-ray disc. And, which means, by the way, that the spiral arms... You know how you see those beautiful pictures of spiral arms and spiral galaxies? The spiral arms are all inside this Blu-ray disc. Like, they're that thin. It really blew my mind when I learned that. It was like, whoa, really? They look thicker in the pictures. But you can't tell.
Gosh.
Yeah, it's pretty cool. Anyways, this is the Milky Way. The bulge is a little bit thicker than that, but the rest of the arms are as thin as the Blu-ray disc. And if you can't tell from Earth because Earth is tiny, right? So it looks thicker, and the thicker bits are the parts that are closer to us, but actually if you look at it from far away, and compare it to the diameter of the galaxy, the thinness is comparable to Blue-ray disk. Okay. All right. Rohit says he knows what a CD is.
I know it.
Gen Z. I'm asking if they're. I don't know. Anyways, I still have old CDs. Actually, in Physics 190, because we've been online. We've been making our own spectroscopes at home, and one of the things that you can, we send them a little grading by mail, but some people were on the other side of the planet, right? Mail just didn't get there. So I gave instructions for creating a spectroscope using old CDs. So they had to actually find an old CD and you just use Scotch tape to remove that foil on the top of it, and then it becomes a diffraction grating. You stick it on top of an old toilet paper roll and put a slit on the other end, and you've got your own spectroscope. It's really amazing. But anyways, that required them to know what a CD was. So unfortunately, everyone who needed to do this knew what a CD was. But anyways, back to, sorry, I'm going really off topic. Here we are. Center of the Milky Way, near the center anyways, is the Swan Nebula, which we're going to look at. So, I have to clear this. And let's take a look at the Swan Nebula. All right. The moon is
yellow.
Already up. It's yellow, but that's because I haven't balanced the colors yet. So why don't you go ahead and try to talk about the Swan Nebula a bit while I try to balance this image.
All right. So Swan Nebula, it gets its name because it looks like a duck. No, but it looks like a bird, and a lot of people say swans. But it is also known as the Omega Nebula, and oh my God, it has so many names actually. Omega Nebula, Checkmark Nebula, Horseshoe Nebula. Just different people see different things, right? I mean, that's how constellations were created in a sense, because people saw things in the sky, saw shapes and things in the sky, and they go, "Oh, let's call it that." Anyway, this is nebula discovered by French astronomer Philippe Lo de Chezeaux in 1745, if I pronounced that correctly, which I didn't. But it was catalogued by Charles Messier in 1764. In the constellation Sagittarius, and it's about 6,000 light years away from Earth. And it spans about 15 light years, 15, in diameter. It's a massive structure in space. But also, the reason why we can see it, and actually this is similar to, exactly like how we can see the Orion Nebula, is that there's a star cluster in it. And all of the radiation and light coming from the star cluster, it reflects and reflects off the nebula, but also that radiation excites the particles that are in the nebula. And what happens is, and this is called spectroscopy, is the light that is then emitted from those excited particles heads to Earth. And that's why we get those different colors. With this one, it's a little tricky to see, but there's lots of reds and oranges. I think the greens are coming from the color balancing. But anyway, lots of reds and oranges, and that's due to the nebula being primarily made of hydrogen and helium, which gives it that. And pretty much now, because it's mostly hydrogen and helium, this type of nebula is a stellar nebula, or the cradle or birthplace of stars, pretty much. All it takes is just a little gravimetric disturbance or something to push the particles together, and that kind of starts the process where now you've created a a spot of greater gravitational influence, and that just attracts more dust towards itself, and eventually, over hundreds and millions of years, that will make a star that will be born. But I think with this star cluster in the middle, what happened is these stars that are in the middle, I think they were formed at around the same time, and actually that's kind of a hypothesis of how like most stars are born, is they're kind of born in a cluster, but then once they kind of start to interact with themselves, they'll slingshot each other out of the nebula or away from each other, and they'll become just their own little stars in solar system. But yeah, the open cluster in the middle, also called NGC 6618, causes radiation, causes the nebula to shine, and it is also one of the youngest clusters known, with an age of just 1 million years. So this, I think, also just supports that this cluster was made kind of all in the same area, and it's we'll get into this in a second when we talk about M13, the Hercules cluster. But you can tell a star cluster's age based on the color of the stars that are within it, with the reds and whites being kind of the older, longer living stars, and with blues, because they're so hot, they burn through their fuel so quickly that they're actually younger stars, and kind of indicative, saying that the star cluster is young. They have a lot of blue, kind of bluish stars, and they'll have a lot of red or white stars if they're kind of on the older side. And also how dense the star cluster is indicative of the age. But with this one, reds, brand new stars, and it's only about 1 million years old, so very young, very young. But how is it looking, Joanna? Is it looking okay?
Sorry, I had to reset it. I realized it wasn't stacking. Now it is stacking. That's because I turned off the line function. But now it is stacking. So now we're getting a little bit more signal to noise. So I'm gonna let it run a little bit longer to see if we can get a little bit more of this. Get a bit more of the image here.
But so this kind of process where it's like the central star cluster illuminates the nebula. It's the same thing happening in the Orion Nebula in the wintertime, where it's called the trapezium, but there's these 4 extremely bright stars that are in the center of the nebula that essentially allows us to see the nebula. That radiation just excites the nebula, giving us those wonderful colors. And also the light just reflects off the dust and gas, and that's how we can see it. It's really kind of cool. Nebula that don't necessarily have a lot of stars in it is harder to see, but there's an example where it's harder to see, and they kind of create like a ghostly little void in space. And if you guys look up like dark nebula on Google, there'll be several examples of. I'm just looking them up. So, dark nebula, where pretty much they're gas. They're still a nebula, but they don't have a lot of stars, if any, in them that allows us to see any kind of structure. They're just kind of absent of light. So kind of spooky, but also kind of cool. Very interesting as well. A famous one is the Horsehead Nebula, which we can only see in the fall and winter because it's it's in the Orion constellation. But that's a famous one, is the Horsehead. Just looking back at the stream here, everything's looking good.
Yes. Yeah, so the star cluster is actually this one here on the left. We're not quite centered on it. But yeah, the stars are born out of nebulae like these. And this is a particularly bright nebula. Unfortunately, the moon is actually rising in the east at the moment, in the southeast, and it's not that far from, right there it is, right there. There's the moon. And I believe that is what is affecting the corner of the image here. That's why I zoomed in, try to get away from the little glare. But you can see the nebula. Actually, I should, maybe I'll zoom, maybe I'll try to move the thing out a little bit more so you can see a little bit of the curve of the, it looks a little bit like a swan, like there's like the neck of the swan is kind of like that. Sorry, not
yeah,
kind of, you know.
I could see it. It looks like a fish, actually, for me, like that little the little teardrop looking thing, and then it looks like a fishtail on the leftmost side. But
yeah,
I don't know. That's me.
Yeah, kind of.
Mm-hmm. I don't know.
Yeah, it's hard to tell. But anyways, there's the nebula, and I thought I'd show you a very young star cluster that formed out of something exactly like this. In fact, it's really close by. There might be a little bit of glare from the moon, but it's a pretty close. It's called the Wild Duck Cluster because of the shape of the stars. This is a star cluster, a very young one that just came out, basically just finished blowing away its nebula around it. And let's take a look at it.
Blowing away its nebula. Oh, like the radiation and solar wind, it blows the nebula away, right?
Yes, exactly.
I'm done. I've got all my material. I'm a star now.
I'm sorry?
No, and blowing away all the
it was
all the nebula. It's like I'm done.
Yeah, this is a very young cluster. It's something like 300 million years old, which is considered really young in astronomy. Like that's a blink of, there it is. There's the cluster. Let me just adjust it slightly. We still have the sky glow, unfortunately, but it's okay. The stars are bright enough that I can fiddle around a little bit. Oh, we're going to align it now this time. Wait, let's do that again. Yeah, so this is the Wild Duck Cluster, and it's because somebody who looked at it, I didn't write down the name of that person. Charles Messier saw it as well, but I don't think he was the one. It's because it's M11, Messier 11. Messier, Charles Messier, or actually maybe I should call him Charles Messier. I'm really terrible at French. But anyways, he created a catalog of objects in the sky that look like fuzzy patches in the sky because he was hunting for comets, and this was one of them. And it's a number 11 in his catalog. It's also called the Wild Duck Cluster. I don't believe he was the one who called it the Wild Duck Cluster. I believe it was somebody else because they thought that the stars made a bit of a V shape. I mean, I don't see a V shape. Do you? I've never seen a V shape in this thing.
I guess like a really, really like thick looking V, like maybe at the kind of at the top of the image, it looks like there's a little U of
like this
of stars, and like a heart shape, I should say.
Yeah.
Like kind of looks like a heart.
Yeah.
But
so they thought it looked like a flock of flying wild ducks. So that was like, anyways, the Wild Duck Cluster. But aside from its name, it is a very young cluster. It was just born out. You can see, right? The Milky Way is this big, huge thing, and there's so many clouds of nebulae, star-forming nebulae like the Swan Nebula. There was the Eagle Nebula right next door. That would be really hard to see, so I'm not going to show you the Eagle Nebula. But all the nebulae, really bright. The Trifid is in here. There are lots of beautiful nebulae in here, which will be hard to see because the moon is right there. And there's lots of highlight pollution too. But that's the full moon. It's very bright. But this entire thing is full of star-forming regions, and this cluster is a star cluster that formed from one of those regions. It is one of the most massive and compact open clusters known. So this is called an open cluster. The reason is because the stars here are not gravitationally bound, or they're only loosely gravitationally bound. They were all born together from the same cloud, but they're only very loosely bound. And once they rotate around, like when they travel around the galaxy, they'll split apart. Eventually, they'll completely split apart, and encounters with other star clusters will cause the stars to move apart. So that's why it's called an open cluster. And this is a kind of a cool cluster because it happens to be near an old supernova remnant, which you can't see here, but it's near one, and it's the supernova. The supernova remnant seems to have enriched this cluster, like the cloud that the stars were born from. That cloud seems to have been enriched by a lot of heavy elements. They're called alpha elements. Now, what in the world are alpha elements? Alpha, it just means, okay, never mind. I won't tell you what an but basically what it means is that the heavy elements that are created when a star, okay, our star, like our sun, is burning hydrogen into helium. And actually, a helium atom is called an alpha particle. So it actually comes from that. But it's alpha elements are not helium. What alpha elements are things that are multiples, where you have lots of helium atoms together to make another atom. Heavier elements like oxygen and carbon and silicon and all those things. Yeah. Alpha elements are the heavier elements that are created. Even heavier than the ones that I just listed for you. Not the ones that are actually multiples of alpha particles. But those elements, okay, forget everything I just tell you. Everything that is the heavy elements that are created just before and during a supernova explosion. Okay, so they're created during supernova explosion and just before, those really heavy elements, right? Just a little bit less heavier than iron. And those elements are created in the evolution of a really massive star. So not like our sun, stars that are more massive than the sun. And anyways, a supernova exploded nearby and spread all those heavy elements in the cloud that formed this cluster. And so you can see the signature of those heavy elements in the stars, in the starlight of the stars in this cluster. So anyways, this cluster is full of stars with unusually high amounts of these heavy elements. That's all I wanted to say about this particular cluster. But this is an open cluster.
Oh,
hope
awesome.
That made sense. Hope that made.
And just a touch on that too, because heavier elements like gold and iron, platinum, and all that kind of stuff, like really heavy atoms, because they exist on the surface of the Earth, and aluminum, all that kind of stuff. It's a strong theory that our solar system, and maybe even neighboring stars that are close to us, were birthed in a supernova remnant as well. I think that's the kind of the current theory. But all those heavy elements, since they're on Earth, that possibly we were supernova remnant, which is kind of cool.
Yeah. Okay, cool. Let's move on. So this was an open cluster. The next cluster we're going to see is a different type of cluster altogether, and this is quite a famous one. We haven't looked at it in a while, I've noticed. So we're going to take a look at this one. This is M13, a globular cluster, which is different from an open cluster. It's in the constellation of Hercules, and you can actually, if you're in a really a good spot with really dark skies, you could actually see this globular cluster with the naked eye if you had good eyes and a dark sky. So not Vancouver. But this is the Great Hercules star cluster, and it's pretty neat because it's quite compact. But Kyle, why don't you tell us a bit about M13 while I get this image going?
Get it going, yeah. So M13. So yeah, dense cluster, really good in Manning Park that I've been to, like the Cascade Lookout, because you're in the middle of
of a forest with like the only source of light being from a campsite or the little main camping ground. Fantastic object to see, and it's naked eye. You can totally see it. Anyway, very compact cluster. So compact that theoretically, if there was a planet orbiting on one of the stars in this cluster, you would pretty much have no nighttime. There would never be a nighttime because the stars are just so close to each other. It's like having multiple suns in the sky all the time. Kind of stressful. But anyway, so Hercules. It is 23 arc minutes in diameter, which is really big because the moon is 31 arc minutes in diameter. So just to briefly kind of talk about like how big an arc minute is in the sky, your pinky finger held at arm's length, or the width of your pinky finger, is represents 1 degree of sky. And then within that 1 degree is 60 arc minutes. And then every 1 arc minute is 60 arc seconds. So an arc second is an incredibly small patch of, or section of sky. But this cluster is 23 arc minutes in diameter, so pretty big, yeah. And the moon is 31 arc minutes, so pretty close to the full moon. Anyway, it is 145 light years in diameter, incredibly massive, with several 100,000 stars, and you know, Joanna and I were trying to find this, but the largest star that is in this cluster is a star called V1554. And oh geez, I'm not sure if we can even see it in this image here, because like the instructions are like to look at a little triangle and it's like a red one. We're just gonna kind of skip all that. It's a red giant star and it's really, really big. Somewhere in the cluster. Anyway, it is 24,000 light years from Earth, so it's actually pretty close, I think, to the galactic center, actually, because we're about 25,000 light years away from the center of the galaxy. And the blue stars that exist in the group, they're called blue stragglers, because they're actually formed from the collision of stars in the cluster. Which is, of course, collisions with stars in clusters like this is pretty common because they're really, really dense. So, yeah, pretty common. And because it's so dense, and there's orange stars and white stars in the cluster, it is actually a really, really old one too. It's about 12 billion years old. Which is pretty close to when our own Milky Way galaxy was formed. I think it was, you'll know this off the top of your head, Joanna, but like, I think it was 13 billion years is how old our galaxy is, or
something like that, yeah.
Something? Yeah.
Yeah, something like
really,
that.
Really old.
Yeah, and globular clusters are pretty old, like they were...
Oh yeah, they're super old. What else was I going to say about this? There is actually, if you look at kind of a more professional photo taken on the internet, there's a galaxy. There's a couple galaxies in its image, and one of them is one called IC4617, and it's actually a picture that Howard took way back when using the observatory. But I don't think you can see it here. It's edge on galaxy, super faint. Yeah, I can't see it. But there's a couple galaxies in the field of view as well. And of course, it's one of the best known clusters in the Northern Hemisphere, which is rivaled by Omega Centauri in the southern, which is the largest globular cluster in the Milky Way. Known, of course, but largest known globular cluster in the Milky Way is Omega Centauri. Can't see it in the northern hemisphere, but if you go down south, you'll see it nice and big. I forget the facts about Omega Centauri. I think it has like, is it close to like 1 million stars or something like that? Or,
yeah, that's a good question. I don't know that off the top of my head.
Oh, jeez. Anyway, something outrageous as well. Another super old globular cluster, but this is a fan favorite. Like going outside, like I look for it all the time when I go out stargazing. But it's really popular, and a lot of people describe it as like a little dash of salt on a black background. You see it for the first time, and it's kind of easy too, because in between the two stars in Hercules, if you're looking for the cluster, oh geez, what are the stars called?
This is Hercules, right here, and these 4 stars make a bit of a keystone in Hercules, right? This is like Hercules' torso, and he's got his arm up and another arm. I don't know. I can't really. I can sort of see
like he's
it,
running.
but there's his torso, and the cluster is right here in between these 2 stars of the keystone. So it's something. It's really bright. It's actually very easy to find in a small telescope if you have one.
Oh yeah.
So globular clusters are different from open clusters in that globulars are gravitationally bound, and they're actually, if it weren't for the fact that they didn't have dark matter, they're almost like their own little galaxies, like tiny little eensy-weensy dwarf galaxies. But they don't have dark matter, so they don't count as galaxies. But yeah, like they're also only like a few tens of thousands of stars, whereas galaxies, that's 10 to the power 4, right? And whereas galaxies are more like 10 to the power of 10. Well, giant galaxies like the Milky Way, but the dwarf galaxies are something like 10 to the 6, like 1 million stars. 1 million stars to 1 billion stars is a dwarf galaxy. But these could be on the lower end if they had dark matter, but they don't have dark matter. It's actually a bit of a mystery as to how globular clusters form. It's like, there are lots of theories. For example, interactions with other galaxies could create these tidal, what are called tidal dwarfs. Maybe in the early universe, since the early universe was really a lot denser, that's how they were formed. But it's still not quite known. It's still a bit of a mystery. So if any of you are out there and are looking for starting off your career, looking for an education, and you want to figure out and do something and solve mysteries in astronomy, well, this is a problem that you could try to solve for us, is how do globular clusters form. It's one of the many mysteries in astronomy.
Oh, jeez.
Yes.
Interesting stuff. But yeah, globular cluster M13, very popular. Yes. Would recommend. 10 out of 10.
Yes. All right. So, should we move on? We don't have much time left. And I do want to show some...
Oh my god, really?
We have a couple of planetary nebulae that I want to show you. And we're not going to get through all of them. But we've got... I don't know. Which one do you want to look at? Maybe...
we see the Ring Nebula. Let's take a risk. Let's go Cat's Eye.
Cat's Eye.
Because that's a really cool looking one.
That's a very cool looking one. It's a very cool looking one, actually. And I know that one works.
Yeah, just... it does work? Like, it's pretty good?
That one we do know works, because I've seen it many times, actually. Okay, this one, hopefully... Okay, we won't look at it that long, but once it goes past the meridian, then something will happen to it. Okay, but that's okay. We will
adjust
things.
Planetary nebula, just a little very quick intro. They're called planetary nebula because astronomers thought they were looking at planets, because they have such a distinctive round shape. So that's why they're called their planets, because they kind of look like it if you were just looking at it. I didn't know what you were looking at. But very cool looking things. A really good, famous one is the Ring Nebula, which really just highlights what a planetary nebula is, where it is still a corpse of a past star, but it didn't go boom like a supernova. It would this red giant would pulse for a few million years, and then its final pulse would just kind of release its outer layers, not in some fiery explosion, but just a little huff that blows it all away.
Huh.
And what's left over is the white dwarf. Uh-oh.
We are looking at nothing. I'm not sure why. Let me try to think about this. Why are we looking at nothing? Now, I know that the cap is not on because there is no cap on this telescope.
Landscape's not on, right? Yeah, again, this is where we should, like the cat's eye nebula is what we're looking at. But,
yes.
See what's going on here.
There's nothing. It's completely black. Let me think.
I'll keep talking.
You keep talking.
Yeah, so planetary nebula. It is, and it's actually the stage of, or sorry, I should rephrase that. It's what our sun will end up as once it dies. A planetary nebula. It'll release its outer layers, and it'll give these awesome colors and enrich the galaxy with all of its heavy elements. Anyway. So, because of that central white dwarf, and just like the Swan Nebula we saw before, the radiation from the white dwarf illuminates the nebula, and that's how we can see the colors with, again, hydrogen and helium being like the reds and oranges. But because it's a star that that formed like heavier elements like carbon and oxygen, it'll also have these beautiful blues and greens that tell you that the oxygen and the nitrogen that were in the center of the star, pretty close to the core. Yeah, so kind of it's this wonderful, pretty thing. And what's left over, the white dwarf, because it's not fusing, like it's not heavy enough to actually fuse its fuel, it will remain white hot for trillions of years, because of course it can't radiate any heat away. It just gives off light. It radiates heat, but very, very slowly. So it remains hot for such a significant amount of time, eventually finally cooling off into something called a black dwarf, which is the last stage of our sun. And it's black, not giving off any kind of heat or radiation, and it's just a ball of matter floating in the sky. And to get to this stage, it takes such an incredible amount of time that it's so far like trillions of years, which is older than the universe has existed for. So currently, we think there are no black dwarfs in the universe because it takes such a long time to get to that stage.
So, guys, the camera has disconnected. I don't know why.
But my God.
That's okay. Let's take a look. Let's use the other camera. It's going to be a black and white camera. It's not a color camera, but it's actually the better one. So, I have no idea why the camera disconnected. That was very, very strange. But that's okay. We have a better camera. But it's just the only thing is that it's black and white. So
that's okay.
Apologies, folks. It will be a different camera.
We have our imagination.
We do. We're imagining
the
screen.
Yeah, and the internet. The internet, yes. But anyway.
Okay, I'll turn on the coolers. Why not? but that's okay. Let's take an exposure already. We can already take an exposure. Luminance filter is good. I think let's do a 20-second exposure. This one doesn't do live stacking automatically, but but it'll still show us something.
Mm-hmm. Something better than nothing.
Yes.
I like that. Yes. Just looking at the chat, Tufts, yeah, do the Hubble fix. Turn it off and on again.
That's right. Okay, where is it? There it is. There it is, right smack dab in the center. Okay, I'm going to try to adjust it a little bit, but whoops. It's really too bad that we don't get to see the colors.
Yeah. Yeah, so for those looking, it looks like there are like just countless stars in the field of view, but those are actually, well, it's just noise, but there's also hot pixels in there too. Those are all those white dots, which...
Look at that! Isn't that so cool? Can you see it,
oh,
everyone?
My gosh. Yeah, I can see that. That looks incredible.
It's black and white, folks. I'm sorry. But I think it's still kind of cool.
I think that looks cool. Looks like there's like two sets of rings, like a vertical and a horizontal.
Yeah, it's pretty neat. Yeah, isn't that so neat? Oh my goodness, so cool. This is a way better camera. The thing is, we can't automatically turn it. So what we normally do with this camera is we take, we take a shot with the blue filter, with a green filter, and with a red filter, and later on we combine them to make a color image. But so that the camera is much more sensitive, and it's also much more. It's just a much better camera. But we have to actually go and post-process the images afterwards, like combine the RGB. We can't do that on the fly using this camera, unfortunately.
So much work.
It is, yeah. It's a lot of work.
No. Very fun, though.
Yes, it is very fun. But at least you can see something in black and white. It would normally be in color. But it's so cool, right? You can see the rings. So apparently the Cat's Eye Nebula has a binary. So it's the reason why it's got these two rings is because of there's probably a second star in there. So one of them. So a planetary nebula is the result of stellar death. Stellar death of a star that's kind of like our sun, and so like low mass stars. And what they do is that they first of all they burn all their hydrogen into helium, and then once they've done that, but only in the core of the star, not the whole star, then it expands into a red giant, and eventually the outer layers of the red giant float away into this beautiful nebula. And rings often form. The planetary nebulae like these they come in all shapes and sizes and in all different colors. I'm sorry we can't see the colors, but they come in all they come in all shapes and sizes, including with these rings. And what's going on here is that there's probably a second star in there that is causing the ring structure. Yes. So one of the stars has evolved into a red giant, and now the outer layers float away, leaving a core behind, leaving the glowing core behind, which has become a white dwarf. But the other star has still not. It's also evolving, but it still hasn't quite become a white dwarf yet. So that's the reason. That's the best hypothesis, the best theory as to why we see these different polar rings here. Or these two different rings. Yeah, so there's a lot of cool things about this particular. I mean, planetary nebulae are so cool. I just love them.
They're always so cool.
Yeah.
And it's like I was saying earlier, all of those heavier elements, oxygen, carbon, aluminum, all that stuff was formed inside a star, and it's in that little those rings, that planetary nebula there. It's all in there, and that nebula could collapse again and make another solar system eventually, but it has the chance to, which is like looking into the future. What possible life could evolve on such places? So cool. Anyway.
Yes, very, very cool. Okay.
What else do I have? I think.
So.
How far away is this thing?
We have.
There it is. Okay. Got it.
We have 10 more minutes left, and I'm wondering if we should take a look. What do you think? We have quite a few more things on the list. Our camera has just disconnected. We only have one. We have this black and white camera left, which is not too bad. It's actually much better. It's got much better resolution and so forth. Mm-hmm. But what do you think? What should we do? Should we look at another planetary nebula, or should we move to Saturn, or what do you think?
Let's look at Saturn. The tried and true. Let's go. Okay. Let's go to Saturn.
Okay, so you'll notice. Okay, you're probably wondering why it's called a planetary nebula. I know Kyle explained that it looks a bit like a planet in the sky. But take a look at this. Okay, I will now zoom out. Wait, I'm gonna zoom out here, and oh no, I'm zooming in. Am I zooming in or out?
Oh, I think you're zooming in.
The mouse wheel. Okay.
Whoa!
Look at how tiny that thing is compared to the size of the image. No.
Oh my god.
Okay, so it's pretty tiny, right? Like the image is actually quite. Okay, so this is the whole thing, and this is there it is. It's right in. Okay, now when we look at Saturn, notice how big it will look on the same image. In fact, I'm going to leave this one open, and we're going to take a look at Saturn, and it will probably not need as big of an exposure, but we'll take a look at Saturn, and we will...
Something as massive as a planetary nebula. It's probably like, I don't know, 5 or so light years in diameter. Well, still looks insignificant.
Right. The Cat's Eye Nebula is something. Did you already say how big it was?
No. I was just giving an estimate.
Okay.
Like,
it's something like a few light years across. Maybe even something like planetary nebulae are usually about like on the order of a light year to a couple of light years across. So that's I mean that's huge. A light year is huge. That's, I don't know, what is that? Let's translate that to something like 10 to the 18 meters or something. 16 meters? I always forget the units.
It's like 16. 9 trillion kilometers or something like that.
It's crazy. Trillions, billions. It's when humans can't even tell the difference between a trillion and a billion.
Really?
Like we just cannot fathom it. We're so puny. We cannot fathom the difference. But they're anyways. So planetary nebulae are huge, and a planet itself is not that big. Okay, so there it is. It's right by, of course, the full moon, and it is 14 degrees in the sky, so we can still see it. So I'm gonna give it a tiny 0.5 seconds, and maybe even that is too much. But let's take a look. And there it is. There is Saturn. So compare that. Hey, where'd the other one go? Okay, but you saw that. It's comparable in size, right? So that's why planetary nebulae are called planetary nebulae, because they're comparable in size to what planets look like. But this planet itself, of course, is much smaller. Like it's eensy-weensy, a speck compared to a planetary nebula. It's just that the planetary nebula was a lot farther away. So let's zoom in on this and adjust the image, and let's take a look at Saturn. I'm going to just adjust it a little bit, but you can already see the cool.
It's beautiful.
Look at that! Isn't that cool?
Oh, yes. Rest in peace, Cassini.
Isn't that cool? In fact, 0.5 seconds was even too much. I'm going to try 0.2. Look at that.
Oh. Yes. Is the top ring in front of the planet?
Yeah, you can see it, right?
And can you tell that? Oh, you can tell it. Yes.
Yeah, I mean, it's upside down compared to the
Right.
view,
Yeah.
I believe. I mean, let's just... because the camera view might have inverted it, but I actually don't remember what it looks like now. My mouse wheels, I never know which
And when we
direction
see it again, from end to end, like from ring tip to ring tip, it's the distance between Earth and the Moon. Like you can fit Saturn in between the Earth and the Moon. Pretty big.
That's right. Yeah, you can fit Saturn between Earth and Moon. Okay, there it is. See, so this is the orientation. So the camera has, like, the optics of the telescope plus camera has flipped the image. But that's there it is. There's Saturn right there. Isn't that so cool? Unfortunately, it's not in color, but black and white is still very cool. I think, like, just to see, like, how the planet is three-dimensional, it just usually kind of, it's so cool. Like, I mean, it, you know, because images of things like nebulae and galaxies, they kind of look flat in the sky, but because Saturn has a shadow and you can see that ring there, you can see that it's really a three-dimensional sphere. I'm going to try 0.1 seconds, see how if that improves the image a little bit. Yeah, it does a little bit.
Oh, yeah, and I also want to touch upon, so remember when Joanna was talking about, like, the galaxy is pretty much a CD in how, like, thick it is, except for the central bulge, of course, but, like, the edges is like a CD. The rings are comparably even thinner. So if the galaxy is like a CD in terms of its thickness, the Saturn is like a piece of paper in its thickness, pretty much. Like the like from the top of the ring to the bottom of the ring is like some 30 kilometers or something. Like so thin that if it's edge on, like if the rings were edge on, they essentially disappear. So thin. Oh, you can see the Cassini division too.
Yes, you can see it. Yeah, it's kind of hard to tell. I wonder if I could even expose for even less than that.
Just looking in the comments here, Lee's saying that maybe you can see Titan if we like zoom out. I don't know.
But the thing is, you have to then expose differently. You have to overexpose Saturn in order to see in order to see Titan. That's the thing. But anyway, that's Saturn. I'll try that again.
Was it 1 billion kilometers away or something?
I don't have that memorized. I don't know. But you know, when I was like, Saturn is, would you say the size of the distance between Earth and the Moon, right? That's so cool.
Yeah.
But another fun thing about Saturn is that it's less dense than water. Like, you can calculate the mass of the planet and you can calculate the volume of the planet, and the density is the mass divided by the volume. So I apologize for the math, but hopefully you remember that from high school science, right? Density is anyways, it's less dense than water. So the point is that if you dropped Saturn into a gigantic swimming pool with the same gravity as Earth, then it would float. It would float in that gigantic swimming pool, which I always thought was so weird. But it makes sense. It's a gas giant. So it's the only planet that is less dense than water. But yeah, it's a cool fun fact about Saturn. I also to end to end our night on a silly note, I heard this great Saturn joke.
Oh jeez.
What did
Oh jeez.
What did Mars say to Saturn? Give me a ring sometime.
Give me a. Oh my gosh. Oh my gosh. Well,
I
we liked it,
apologize.
so we put a ring on. So
Oh.
I heard that somewhere, and I thought that yes, exactly.
Okay, yes. All right. All right. It is now 11:30, which marks the end of our evening, unfortunately. But hey, we got to see quite a lot today, hey? We got to see stars, colorful optical or gravitational binary star, Alberio, remember the two stars that had different colors. We saw some nebulae, and we saw some star clusters, and we saw a planet. So we got to see quite a lot tonight. So thank you all for joining. This has been really fun. Thank you to our moderators, Zach, Rohit, and Douglas. And Kyle, thank you so much for joining me. This was really a lot of fun.
Of course, this was so much fun. Thank you for the wonderful show.
Yes.
I enjoyed it.
And thanks, and I apologize for some of the technical difficulties that we had tonight, but we still got to see some fun things. So, by the way, Saturn, if you're still awake and you want to see Saturn is visible to the naked eye. So it's really bright. Like it's you'll see it. It's even though the moon is out. Where's the full moon? Let me just show it to you. There's the full moon. The full moon is really bright, but just to the left of it is Saturn. You can still see it. It's a very bright star. It's brighter than all the stars around it. So that's the brightest star you see near the moon. That's going to be Saturn. And Jupiter will be coming up later in the night. Jupiter may already be up, actually. But later in the summer, we'll be able to see Jupiter come up. And Jupiter is incredibly bright as well. So that'll be fun to see later in the summer when it gets high enough for us to see for starry nights. But yes, thank you. Thank you all for joining us. And please join us again for future virtual starry nights. We do this every Friday night on a clear night. And we are so far doing it all online, which is really fun because then you don't have to line up to see every object. You can just watch in the comfort of your own home. Which is kind of fun. But on the other hand, in-person starry nights is also really fun, and because you get to be together with everybody, and people from the Royal Astronomical Society bring out their telescopes, and it's really fun, everyone talking about space. I don't know when that's going to happen again, so we're in conversations with the authorities that be on campus, and hopefully we'll be able to do it again soon. But we will announce when we are able to do it. I will definitely announce it to the email list. If you're joining from Facebook or Twitter, sign up to our email list so you can get the announcements of when these events happen and when we will resume in-person starry nights. So you can find...
We miss
Sorry, go
all
ahead.
your faces.
Yes, we do miss all your faces. So you can find that you can sign up for it. You go to our website, look up Google Trottier Observatory, and you'll find the website, and you'll find the how to subscribe to our email list. So yeah, thank you so much. So keep looking at the skies, and clear skies to all of you. Have a good